All right, let's go over these. Okay, so resonance, something we went over at the end of the class on Friday. Right, these are the rules for resonance that we'll touch on as we go over these resonance structures. Right, the one thing that I want to say, right, with resonance structures, they're always going to be the same formula, all right? And they're not going to break any of the rules that you've learned so far with regard to bonding, with regard to Lewis structure, and with regard to electron count. Right? The only electrons that we're moving around on these structures are electrons in the pi system. Right? So that means pi bonds, formal pi bonds, or non-bonding electrons that are conjugated to a pi system in a p orbital. All right? And then with charges, you want to make sure that charge is conserved, right? So if your molecule that you're starting with is positive, all resonance structures that you draw have to be positively charged, right? If the formal charge of the molecule you're drawing resonance structures for is negative, all resonance structures have to be negatively charged, right? If it's neutral, all resonance structures have to have a net neutral charge. Okay. All of the resonance that you draw, 95% of the resonance that you draw can be taken from these two examples, right? The allyl-anion and the allyl-cation. The allyl-anion, right? What you're looking for is a pi bond, right? That is one sigma bond removed from an element with a non-bonding pair, right? So if you look at this system up here, we have our pi bond. Right? We have that attached to a sigma bond, and then we have on that sigma bond an oxygen with two non-bonding pairs of electrons, right? So this is an example of this allyl-anion, even though this is not an anionic system, right? We have our double bond, single bond, and atom with lone pair. All right? The other system is the allyl-cation, right? Where we have a double bond, a single bond, and then an empty orbital that would be empty p orbital would be in that place, right? So something that the electrons can go into. You can see with the allyl-anion, when we push electrons, when we draw the mechanism for this resonance, we're pushing from the atom with the lone pair, right? So we're showing these electrons make a new bond, right? And the pi bond, those electrons come out and become a new lone pair of electrons, right? So the arrow flows, or the arrow direction flows from the atom with the lone pair of electrons toward the pi system. When we're looking at the allyl-cation, right, now we're pushing towards that empty orbital. So we're taking pi electron density and pushing that toward the empty orbital, right? So what this is showing is that these electrons, right, which are bonded between or shared between these two carbons, staying with the carbon in the middle, making a new bond to the carbon at the end, right, and leaving the carbon at the beginning. Okay, questions about this? Okay, so most of what we draw in resonance can be distilled down into these two systems, right? We just have to find, those systems in the larger molecules that we're playing with. All right, so first resonance structure, right? We're going to draw this just like we did on the allyl-anion. We're going to take an arrow, show how those electrons on the oxygen are forming a new pi bond, right? We have 8 electrons around this carbon already. So if we're making a new bond from oxygen, we have to push 2 electrons out, right? We can't get 10 electrons around a carbon center. So if we're making a new bond, right, we have to break an old bond. And so draw a resonance arrow. There should now be a double bond between oxygen and carbon. Oxygen should have a formal positive charge, right? And then those pi electrons are now, rather than being shared between carbons, right, those are located or isolated onto one carbon, formal negative charge on that carbon. And everything else should be in place. Okay, so what these arrows are showing right, the arrow that we're drawing from oxygen to carbon, or the oxygen to the bond, is showing the formation of a new pi bond. second arrow shows the breaking of the old pi bond, right, and the formation of a new non-bonded pair, right, or taking those two electrons in a bond and making them just sit on one carbon as a non-bonded pair. All right, questions about this? No? Okay, so if we just continue this, right, you can see we have an atom with a lone pair, a single bond, and then that single bond is attached to a pi bond, right? So we're just going to go around, right, store those electrons on another carbon. Okay, you can see I drew the same number of arrows. Those arrows are communicating the exact same thing, right? One arrow is showing the formation of a new pi bond using a lone pair of electrons, right? The other arrow is showing breaking of an old pi bond and the formation of a new lone pair on a different carbon. Right, and then we can draw one more, put those electrons out on the end to the right. Okay, so you're seeing to get to this third resonance structure, right? Same exact arrow pattern. Okay, I take the arrow from the lone pair, draw that into the bond to show the formation of a new pi bond, right? The second arrow I'm drawing through the pi bond on the outside of the bond, right? And that arrow points to the carbon that gets the electrons. Questions about this? Okay, what's the net charge of the molecule that I'm starting with? Zero. What's the net charge of each of the resonance structures? Zero, right? Very important, right? You can't be just creating a positively charged resonance structure from a neutral molecule, right? Make sure that your charge is conserved. Okay, any questions about the top example? Okay, bottom example. So this would hold more closely to the allyl cation, right? You can see we have a double bond here, right? And that double bond is a single bond removed from an empty orbital, from a positive charge, right? So we can show in the allyl cation system, we're only showing one arrow, right? We're showing the shifting of pi electrons, right? Between two atoms, and then the shifting of the charge. Yeah?
Can you start with the other double bond?
We could. Yep, yep. All right, so you can see there's a pi bond between these two carbons. Okay, we're breaking the pi bond to the carbon on the bottom, right? And making a new connection to the carbon that has a positive charge. So if we're breaking the pi bond away from the carbon on the bottom, that's the carbon that now gets a positive charge, right? Because we're taking two electrons away to make a new bond to another atom. Questions about this? Question about what the arrow means. Okay. Right, we could have started, if we wanted to, we could have started with this pi bond, right? So we're just going to show this move over, and that one pushed back down, right? So in this resonance structure, to get to the next resonance contributor, right, we're showing two separate pi bonds move, right? One to kind of get us back to where we started, right? And then the other one to show us a new unique resonance structure. So we usually try to show just one, right, the movement of those pi electrons just once. Okay, because here we would show movement of pi electrons once would get us back to the beginning, right? We're showing the movement of two separate pi bonds. Okay. Questions? Okay. And final one, so this is the one type of movement that does not conform to an allyl-anion and allyl-cation system, right? And that's whenever we have a positively charged carbon, right? Carbon with an empty orbital next to a heteroatom with a lone pair, right? And all that's going to happen is that the heteroatom is going to reach over and bond to that carbon with the empty orbital. Right? And so that gives nitrogen a formal positive charge. Questions about this? Yeah?
Could you have done that last step in the first resonance structure? Like combine them?
Could I?
Like have moved the non-bonding pair on the nitrogen?
Sure. So, I mean, technically, right, when you draw resonance structures, you can show as many electron movements as you want. I, encourage you to really keep things simple, right? And try not to move, unless you have to, try not to move more than 2 bonds, right? So for the allyl-anion system, we draw 2 arrows, right? Showing the formation of a new bond, formation of a new lone pair, right? Allyl-cation system, we're showing 1 arrow, and that's shifting of pi electrons. Here we showed 2 because we had to, I didn't want to redraw this, right? So this shows going back to the original, right? And then formation of a new structure, moving those pi electrons, right? But we could also, if we wanted to, we could show those electrons move, right? And then we would have to represent this structure, right? So the arrows kind of show us, they're a map, right? They show us where the electrons were and where the electrons are going. And so they more or less tell us what structures we need to draw. Does that answer your question?
Yeah.
Why are we ignoring the double bond at the very end?
It's a good question. Does anybody want to answer that?
It's not conjugated.
Excellent. It's not conjugated, right? These electrons here are not conjugated with that pi system because there's an sp3 hybridized carbon in between. Right? So I put that there on purpose, right? For you to say, oh, there's a double bond, let's move that one around. But remember, in order to move the double bond around, it has to be conjugated with pi electrons. Questions? Okay. Okay, so we're going to spend the rest of this class talking about aromaticity. Okay, so to understand aromaticity, we need to understand the energy of different systems that have double bonds in them. All right, so first I want to take a look at cyclohexene, right, and consider the heat of hydrogenation for cyclohexene, right? And all the heat of hydrogenation is this reaction would be called a hydrogenation, because essentially we're adding H2 across that double bond, right? We're replacing a carbon-carbon pi bond with 2 carbon-hydrogen sigma bonds. Okay? Pi bonds are higher energy electrons, right? Electrons in pi orbitals are going to be higher energy electrons than electrons and sigma bonds. So this is a higher energy molecule than this molecule, right? So whenever we do this reaction, this is going to be an exergonic reaction, right? A drop in energy. And so the delta H for this system is going to be around negative 120 kilojoules per mole. Okay, so that's how much stronger the two carbon-hydrogen sigma bonds are than the carbon-carbon pi bond that we're losing. That's all that means. Questions about that? Great. Okay, if you had to guess the heat of hydrogenation for a 6-membered ring with 2 double bonds, what would your guess be? Right?
Double that of the original.
Yeah, approximately double of the original, right? And so in this case, this is going to be about negative 235, let's say 230 actually, kilojoules per mole, right? So roughly double, okay, a little less. Okay, if we take benzene, right, based upon what we see here, we would maybe predict that benzene would be roughly 360 kilojoules per mole for the heat of hydrogenation. Right, but the delta H for this system is 208 kilojoules per mole. All right, and so what this is showing is that benzene is going to be much lower in energy, right, than what is predicted by this trend. Right, 1 double bond, 120, right, 2 double bonds, roughly double at 230. We get 3 double bonds in that 6-membered ring, right? Now that energy is not equivalent, right? It's less energetic, right? Lower energy than this system here, right? Despite having more pi electrons. Okay, and that's because this system is stabilized by aromaticity. Right, it's an aromatic system. Right? If we look at benzene, we have to understand the structure of benzene, right? 6 carbons. All of the hydrogens are radiating out from the middle, right? So all of those sigma bonds are going straight out from the center. But the pi electron density in this system, those 6 pi electrons, exists above and below the plane of that ring. Right, so we have 6 pi electrons, and those 6 pi electrons are all going to be shared equally among all 6 carbons, right? So we draw benzene with 3 double bonds, right? We've talked about this briefly before, but in reality, right, those 6 pi electrons represented by those 3 double bonds are not isolated between, 2 carbons, but they're being shared equally among all 6 carbons. right? So a more accurate way of drawing, representing benzene right, would be like that. Right? Show that we have 6 pi electrons, there's no double bonds in benzene, right? There's just a larger pi system. For this specific pi system, we can define it as being aromatic. Okay, so there are going to be 4 qualities of aromatic systems that we will use to help us identify systems that are aromatic from systems that are something else, right? Not aromatic or anti-aromatic. Okay, so the first rule is that what we're looking for when we're trying to identify an aromatic system is we're looking for a ring, right? It's got to be a cyclic system, and there have to be pi electrons in that cyclic system, right? That doesn't necessarily mean a pi bond, right? Often that's how we would identify things, right? All it means is that there have to be pi electrons, so they could be pi electrons in a p orbital, okay? Most of the time, there will be a pi bond, so it'll be relatively easy to identify. The pi bond has to be part of the ring, right? So if there's a pi bond outside of the ring, that doesn't count. Pi bond or pi electrons have to be part of the ring. Okay, rule number 2, problem number 2, all ring atoms have to have a p orbital, right? What does that mean for the hybridization of the atoms in the ring? Good, right? So that means that the atoms within the ring have to be sp2 or sp if we have a big enough ring. Okay, all the p orbitals of those atoms in the ring, they have to align. All right, they have to be able to overlap to talk to one another. Right? If all of the p orbitals in the ring align, what does that mean for the geometry of the ring? Excellent, yeah, so the ring has to be planar. Right, so all of the atoms in the ring have to be in the same plane. And then the 4th rule, and probably the most important for aromatic systems anyway, is that the pi electron count has to follow what we call Huckel's rule. Huckel was an old German chemist back in the day who helped contribute to the discovery of benzene in aromatic systems. And what Huckel's rule says is that the number of pi electrons in the aromatic system has to be equal to 4n minus 2, where n is a whole integer. So 0, 1, 2, 3, right? So no 0.5s. Okay, if there's a 0.5, then you cannot consider that system aromatic. Okay, so as long as the system follows rules one through 4, qualifies as being aromatic, right? If a system follows rules 1 through 3, but breaks rule 4, right, then we'll consider that system anti-aromatic. Anti-aromatic is as good as being aromatic is. Anti-aromatic is bad, right? It's on the opposite side. It's an element of instability. Frank, yeah.
For Google's rule, did you mean 4 and minus 2 or plus 2? You said minus 2, but you were plus 2.
It should be 4 and plus 2. But yeah, if I said minus, I misspoke. Questions? All right, so let's apply this to a couple of different systems. Okay, so here's an anion, cyclopentadienyl anion, right? And I want to know whether or not this is aromatic. Okay, so just raise your hand if you think it follows the rules as we go through them. So is this a cyclic system with pi electrons? All right, everybody's hand should immediately, like, you know, that's pretty evident, right? We have a 5-membered ring, okay, and we have 3 sets of pi electrons, or 2, potentially 3 sets of pi electrons in this ring. Right? All ring atoms must have a p orbital. Right? How many people think every ring atom has a p orbital? Okay, right? So for this, right, this, and that carbon, it's pretty evident that those are sp2 hybridized. Okay, what about this carbon here?
Yes.
How do we know it's sp2?
I usually consider the number of bonds it has,
Okay.
that many hybrids.
So let's put our hydrogen in there. All right, we'll pair it back. Formal charge. And how many people think sp2? How many people think sp3? Okay, so remember, this is where we need to consider that we need to, when we're looking at electrons, we need to consider whether or not those electrons are conjugated, right? If they're conjugated, or they can be conjugated, then they will be, because that lowers the energy of those electrons, right? So from your chapter 2 perspective, you would look at this and say that's an sp3 hybridized carbon. But now from your new chapter 5 perspective, you want to look at this and say I have a pair of electrons, but those electrons are conjugated to a pi bond, right? And the only way that they can be conjugated to that pi bond is if they're in a p orbital. As such, these have to be this has to be an sp2 hybridized carbon, right? So you need to take on this new perspective of looking for electrons that could potentially be conjugated, right? And what the orbital consequence is for that conjugation. Okay, so all the atoms in this molecule are sp2 hybridized. This is a planar system. How many people think it's going to be planar? Okay, how do you know?
I mean, we're looking at aromaticity, so I was assuming that you probably give us an example that would be planar. But I would say because everything is sp2, and the p orbitals will all be conjugated.
Okay.
Probably a pretty good indicator.
Yeah, if we can identify every atom as sp2, right, then it has to be planar. The other thing is small rings with pi bonds are usually planar. Right, and so we'll say small rings meaning less than or equal to 7 atoms. Right, anything above that it's hard, you know, if they can bend out a plane if they want to. All right, so we'll say that this is planar. All right, and then rule 4, how many pi electrons do we have?
Six.
Total pi electrons, 6, right? 2, 4, 6 pi electrons. Is that a Hückel number? What is n? Or yeah, what is n if we total number of electrons is 6? Yeah. 1, right? And that follows Hückel's rule. Okay, and so we can identify this system as being aromatic. Right, so 6 pi electrons equals 4n plus 2. 4 equals 4n, n equals 1. Questions about that? Okay. Right, I want you to tell me whether this is aromatic or not. Maybe 20 more seconds or so. Okay, so cycloocta tetraene. Okay, is this a cyclic system with pi electrons? Just raise your hand if you think so. Good. Is every atom in this molecule a p orbital? Good, so everybody should be able to identify each of those carbons as sp2. Is this molecule planar? How many people think it's planar? How many people don't know? Okay, that's good, right? I said 7 atoms or below, right? Those cyclic molecules will be planar. 8 and above, we're not sure, right? It kind of depends upon whether that system is aromatic or not, right? So we're going to put a question mark here and just move on to rule 4. Okay, does this satisfy Hückel's rule? No, right? So we have 8 total pi electrons equals 4n plus 2. That means n is going to be 1.5, right? And so does not follow rule 4. Okay, if we say that cyclooctatetraene is completely planar, right? All 8 of those carbons are in the same plane. This system would be anti-aromatic. Anti-aromaticity is a really high energy state, right? It's higher than a non-aromatic system, right? It's very bad, very reactive. Okay, and so what cyclooctatetraene does to prevent itself from being anti-aromatic, it actually adopts a shape that is not planar. This actually. And so cyclooctatetraene is in that kind of boat or folded shape, so it can avoid being anti-aromatic. Okay?
So if that molecule had less than 7 electrons, then it would be anti-aromatic?
If it had less than 7 electrons,
I mean, like when you said.
less than 7 atoms
Yeah.
in the ring. Yeah, so that's a good question. So if we had a smaller molecule with 8 pi electrons, then yes, that would be anti-aromatic. It's hard to do that, though, right? We're getting a lot of electrons in a very small ring. So. All right, questions about this? All right, so as a result, cyclooctatetraene is not aromatic, right? It's not anti-aromatic, so this is just like any other molecule. Right, we would just define it as being non-aromatic. Right, aromaticity is good, anti-aromaticity is bad, non-aromaticity is just one. Rachel.
Without knowing that it would like change to be that shape, so it would be planar, how could we look at this and just know that that's
So if a system can become aromatic, you know, if it doesn't necessarily follow one of these rules, but it can become aromatic by changing, so it does, then it's going to, right? Aromaticity is that good of a quality that molecules will, you know, adopt the structure that they need to be aromatic. Likewise, anti-aromaticity is so bad that if something is going to be anti-aromatic, it's going to probably try to break one of these other rules to avoid being anti-aromatic and just be a regular non-aromatic molecule. Okay. Other questions? Still about 5 minutes left. All right, so see if we can really quickly identify these as being aromatic or non-aromatic, or anti-aromatic, I guess. All right, just because we're running out of time, let's go over these. All right, so the molecule up top. So I chose these two for a specific reason, right? Both of these rings contain nitrogen, right, as one of the members of the ring, and both of them, on both nitrogens, there's a lone pair of electrons, right? So we have to understand where that electron pair is and whether or not it's participating in the aromatic system, right? So number 1, ring with pi electrons, right? Quality 2, all atoms are sp2 hybridized. How many people see that? Yep. Every atom in this has a pi bond, so it has to be sp2 hybridized. It's going to be a planar system. All right, and what about number of electrons? How many electrons are in the pi system? How many people think 6? How many people think 8? Okay, remember the pi system is above and below the ring. What orbital are these electrons in?
P orbital.
Not a p orbital. Nitrogen is sp2 hybridized, but it's using its p orbital to bond to carbon. Right? sp2. Right? So those electrons are sticking outside of the ring. They're not part of the pi system. Right? They're on nitrogen, but they're not in an orbital that's available to the pi system. So this still only has 6 pi electrons. Right? And it's going to follow Huckel's rule and be aromatic. Right? Right? All that time we spent going over orbitals and where electrons are in orbitals, this is how we're applying it, right? We need to understand where that electron density is. Okay, number 2, ring with pi electrons. Okay, quality 2, it's a, every atom is going to be sp2 hybridized. How many people think every atom sp2 hybridized? Okay, what about nitrogen? Why would we qualify that as sp2? Yeah.
Because it's conjugated.
Good, it's conjugated, right? So now we have a lone pair of electrons that's conjugated to 2 different pi bonds. Okay, so these electrons are going to be in a p orbital. And as such, they can be part of the pi system. Right? It's a small ring, everything's sp2 hybridized, so we would expect it to be planar, right? Now for Huckel's rule, because these are part of the pi system, we count those as part of the total pi electron count. So how many pi electrons are there? 6, right? 2, 4, 6. Right? Follows Huckel's rule. Okay, any questions about aromaticity? All right, so this takes us to the end of chapter 5. We'll pick up with chapter 6 on Wednesday. Just like last Wednesday we had an exam, I'll give time at the beginning of class for you to ask questions.